Good morning. In today's lecture, we're going to focus on sections 4 and 5 in chapter 12, where we look at the phase changes between the three phases of matter. So those transitions between gases and liquids, liquids and solids, and so forth. So we're going to start by looking at the transitions between gases and liquids, and we're going to look first at evaporation. And so let's remind ourselves that the evaporation, right, is the change from a liquid into a gas, right? So this is what we call vaporization or evaporation. And so we can look at some of the things that will affect how fast molecules will vaporize or evaporate. The first one here is surface tension, surface area. So this is the idea that if we have more molecules at the surface, then evaporation will occur faster. Now, why is that? Well, first of all, only molecules at the surface have the ability to evaporate, right? And so the more molecules you have at the surface, the faster that a sample of liquid will turn from that liquid into a gas. So for example, if you take a glass of water and put it out in a room, and you take the same amount of water and put it into something like a pie plate or a big dish where there's a lot of surface area, it will evaporate faster. The second factor that can affect how fast something evaporates is the temperature, right? So the higher the temperature, the faster that evaporation will occur, right? Because those molecules are going to be moving faster, they're going to have more kinetic energy, and it's going to be easier to break the intermolecular forces. Now, I will use this IMF throughout the chapter to abbreviate those intermolecular forces that we talked about in the first section. And so higher temperature, easier to break the intermolecular forces, faster evaporation. Now, another factor that will increase the rate of vaporization is the strength of intermolecular forces. So this is how we're going to tie this back to the intermolecular forces that we talked about in the first section, is that molecules with stronger intermolecular forces will have a harder time evaporating and will evaporate slower than molecules with weaker intermolecular forces. So for example, we know that from experience that gasoline evaporates faster than something like water, and that goes back to the idea that gasoline has weaker intermolecular forces than water does, and so it evaporates more quickly. It's easier to break those intermolecular forces, and therefore easier to make that transition from the liquid into the gas phase. Now, the terms that we use for this, at least in a qualitative way, is that a liquid that is easy to evaporate is called volatile, and liquids that are not so easy to vaporize are called non-volatile. So gasoline would be considered a volatile liquid, whereas something like water might be considered less volatile. Now, because those molecules on the surface are held less tightly than those to the interior, right? There's fewer, if we remember, fewer intermolecular forces here. They're going to be the ones that are easiest to break away. And so that's why we see the surface molecules being the one that evaporates and not the interior molecules, which have more intermolecular forces. So, evaporation. Now, if we turn our attention to the opposite process, right, the condensation, and of course, this is the change from where a gaseous molecule is converted back to the liquid state. So it condenses from the gas back into the liquid. These are opposites, right? So they're occurring They are the same change, but in opposite directions. So evaporation from the liquid to the gas, condensation back from the gas to the liquid. So we consider them opposites. Now, at some point, when we have a sample of liquid and gas in a container, right, they will reach a point of what we call dynamic equilibrium. And we'll look at this in picture form on the next slide. But what dynamic equilibrium means is that the number of gas molecules above the liquid remains the same. So we reach, if you will, a steady state, a point where there is no more, you're not going to continue to increase the amount of gas above the liquid. It reaches a certain point and then it won't change anymore. And this is because the processes are going back and forth at the same rate. So in other words, every time a new molecule evaporates, one condenses to take its place. So it keeps everything the same. Now, another term is what we call the vapor pressure. And this is, of course, the pressure of the gas above the liquid. So remember from last chapter that anytime we have a gas, we have to think about the pressure, right? Caused by the collisions of those gas molecules with the surroundings. So the vapor pressure of something is the pressure of the gas above the liquid. And this vapor pressure will increase or become higher with increasing temperature, right? Because increasing temperature, as we saw the last slide, causes more evaporation. So we're going to get more gas, which is going to lead to more vapor pressure. And of course, decreasing or lower strength intermolecular forces will give you higher vapor pressure samples. So something that, like gasoline that we talked about, that evaporates fairly easily because of its weaker intermolecular forces, will have a higher vapor pressure than something that evaporates more slowly, like water. Right? So the weaker the intermolecular forces, the higher the vapor pressure above a sample is going to be. Now, there is no effective surface area. Right? And so, while surface area will affect how fast something goes into the gas, right, you won't affect when this dynamic equilibrium occurs. So the vapor pressure above a cup of water under a given set of conditions will be the same as the vapor pressure above a pie plate of water. You know, they'll both get to the same point. One will just get there faster than the other because of the faster evaporation with the higher surface area. But the surface area itself won't affect the vapor pressure that builds up. So let's look at this a little bit in picture form to try to describe what's going on. So we start out here with a closed system. So we start out with a sample of water in our closed system. And initially what we know is that if I put this water in here, it will start to evaporate, right? So as this container is closed, right, the gas will stay in the allowed area. And so evaporation continues. As you start to build up some of this, you get some condensation to occur, right? Some of these molecules will collide back with the surface and recondense. At some point, you reach what we referred to as dynamic equilibrium, right? Where the amount of this vapor reaches a point where it doesn't change anymore, because every time you add a new molecule to the gas phase, you lose one back to the liquid phase. So what we say is the rate of evaporation equals the rate of condensation. Now, not the amounts, right? What we see is that once we reach this point, the amounts don't change, but the amounts are by no means equal. What's equal is the rate of change, or how fast evaporating and condensation occurring. So they're occurring at equal rates. So again, if one molecule evaporates, another one condenses to replace it. So the net is that we see no changes Even though there's constant evaporation and condensation, we don't see any change in the amount of gas or liquid because of this state of dynamic equilibrium. So we've all heard of boiling, and we often sort of use this interchangeably with the idea of evaporation. But boiling is a specific idea, and we're going to look at what it means when a sample reaches its, quote, boiling point. Now, what that means is that there is enough thermal energy, right, to cause water molecules in the interior to vaporize, right? So if we remember, normal evaporation is only surface. But once boiling occurs, once we reach the boiling point, now any molecule within this sample, whether it's at the surface or in the interior, can evaporate, can make that change from a liquid to a gas. And so when you see these big bubbles, like we get what we call a rolling boil, right? These are bubbles of water vapor, right? If we're boiling water, right, that water has vaporized in the interior, and those bubbles filled with water vapor or steam rise to the surface and then pop, right? And so that's what these bubbles are. It's the gas formed by evaporation of these interior water molecules. And so the boiling point of a material is going to be directly linked back to the intermolecular forces. So the idea is that if the intermolecular forces are higher, right, or stronger, we're going to have a higher boiling point, right? It's going to be harder to get these interior molecules to evaporate the stronger these are. So we're going to have to put in more energy, and so we're going to have to go to a higher temperature. So samples with stronger intermolecular forces will have stronger boiling points, and that'll be something that we use as we go through the chapter. So that's boiling. So now what I want to look at is something called the heating curve. Right? So we're going to look at least part of the heating curve right now, and then we'll look at the full heating curve later on in the chapter. So this is a way that we can track temperature versus the amount of heat added, right? So if we follow a liquid sample here, right, and we say start our liquid at 20 degrees and we heat it up. So we put it on the stove or we put it on a Bunsen burner, right, and we add heat. Right? What we initially see, right, is we see this increase in temperature, right? So we're adding heat, the temperature keeps building up, and depending on the liquid, at some point we reach the boiling point. Right? Now for water, of course, that boiling point occurs at 100 degrees if we have 1 atmosphere of pressure. So under normal atmospheric pressure, water boils right at about 100 degrees. Now we've sometimes noticed that water will boil slightly above or slightly below, and that has to do with variations in the atmospheric pressure, right? If the atmospheric pressure is a bit high, the boiling point will be a little higher. If we have lower atmospheric pressure, the boiling point will be lower. And so it's not always exactly 100 degrees, but very close. Now, the big thing to point out on this curve, though, is once we reach this boiling point, so for water 100 degrees, we see that the temperature no longer increases. Okay? And the reason for that is because all of the thermal energy that we're adding, right, doesn't make the molecules move faster anymore, right, which would result in higher temperature. What it does is it breaks the intermolecular forces that are holding these molecules together. So all of that energy that you're adding is breaking these molecules apart, causing them to go from the liquid phase to the gas phase, or in other words, for that boiling or evaporation to occur. And that will remain the same until all of that liquid has transferred or transitioned into a gas. Once we have only a sample of gas or steam, then the temperature of that steam can rise again, right? And so gaseous water or steam, right, can get much hotter than 100 degrees. But a liquid sample of water, that liquid can never rise above the boiling point. So I want to turn our attention now to the energetics of vaporization. So previously we introduced these terms, endothermic and exothermic. And so we're going to characterize these processes as endothermic or exothermic. So first of all, evaporation is endothermic, right? And remember, endothermic means, right, it absorbs heat. And so in order to evaporate, our liquid must absorb heat from someplace, right, from the surroundings. So this is typically why, that heat is either going to be absorbed from the surrounding materials at their high temperature, right, to get that energy in order for this process to occur, right? So evaporation is endothermic. And again, that's because we're breaking molecules, right? We're breaking these intermolecular forces. Now, one place we've seen this, right, is in evaporation of sweat from our skin. Right? We sweat, that sweat evaporates off of our skin, and in order to do that, that water had to absorb some heat from our skin, giving us a net cooling of our skin, right? So the temperature of our skin will drop down because we're transferring some of that thermal energy into the water as it evaporates. And so we get what's called evaporative cooling, right? And we use this as a way to regulate our body temperature, right? As we sweat, it evaporates, it helps keep our body cool. Now, when we can't do that effectively, right, say when it's really humid outside, right, we can't regulate that. So if this evaporation doesn't occur fast enough, we can overheat, right? We can get, heat stress or heat stroke and under extreme effects. But again, one of the conditions this might occur in is if we have very high humidity. This slows down evaporation because there's already a lot of water vapor in the air. And so it's harder to put more water vapor in the air because, remember, the vapor pressure doesn't want to go any higher. So when air already contains high amounts of water vapor, the sweat does not evaporate nearly as easily, making the cooling much less efficient and potentially leading to, physiological effects like heat stroke and so forth. Now, if we look at the opposite process, right, condensation, it's exothermic, right, which makes sense. If one direction is endothermic, right, so if a gas going to a liquid is endothermic, then the liquid going back to the gas must have to be exothermic. So if one direction absorbs heat, the opposite direction must release heat. And so when it condenses, right, the water releases heat into the surroundings. So as steam condenses on our skin, right, it releases heat, causing a heating up of our skin or a burn, right? So if you hold your hand over steam, right, it's hot, but you can if you had, a liquid at a little bit hotter than 100 degrees, it wouldn't burn as bad, but this is even worse because as that warm steam that might be well over 100 degrees hits your skin, it releases heat into your skin as it cools down, as it condenses, which causes even more heat or more heating, or can, if it's hot enough, lead to burns. We've all probably experienced the idea of water condensing overnight. Right? So as the temperature cools down, and if there's a lot of water vapor in the air, that water will condense. Now this happens normally on coastal cities where there's a lot of water. Right? We have oceans or even large lakes, right? You get a lot of water in the air. That water will condense, pulling heat out of the air as it does so, releasing heat into the air as it condenses, and keeping the temperatures from getting too cold at night. Right? Now, we see similar effects like in the summer around here with the higher humidities. So as the temperature starts to drop, that water vapor in the very humid air will condense, and we see that dew on all the grasses. But what that also does is keep the temperature from getting too cool overnight, and we get these nights where it never really cools down. And so you get that uncomfortable sleeping weather, right? If you were to, have the windows open, right? The temperatures, even though it's dark out, never really drop too cool because of that, all that evaporation or all that condensation that is occurring, getting heat back into the air. Now, of course, we see the opposite in deserts where there's very little moisture in the air, very low humidity. They can be extremely hot during the day and get very cold at night. So we can see large temperature swings from day to night in desert environments, right? They can get very hot during the day, but then when you take away that source of heat, the sun, we can get a lot of cooling because there's no moisture in the air to condense to put heat back in. So we get a greater temperature drop. Now, so we can talk about these in a qualitative way, but we can also do some small amount. We're going to just do a little bit of quantification of these, and we're going to work with a value called the heat of vaporization, or the delta H of vaporization. And this is the amount of heat that's required to vaporize 1 mole of liquid. So if I take 1 mole of my liquid, the amount of heat that I need to add to get it that 1 mole to vaporize is its delta H of vaporization. So let's say for water, right, to evaporate 1 mole of water, or about 18, let's do that again, about 18 grams of water, right? To get 18 grams of water to evaporate 1 mole, right, takes about 40.7 kilojoules to mole if we're doing it at 100 degrees. Right? So if we're at the boiling point, it'll take 40.7 kilojoules that we'll have to add to get that 18. So if we imagine that flat portion on our heating curve, right, we would have to add 40.7 kilojoules to go through that flat portion on our heating curve if we had 18 grams of sample. Now, this is an extensive value, right? So if I have 2 moles, it's going to take twice as much, right? So the more we have, of course, the more heat we're going to have to add to get that larger amount to evaporate. Now, you'll notice it's a positive value because it's endothermic, right? So that means we have to put heat in to get it to happen. So we're adding this much heat to get the process to occur. So we have a positive value. Now, of course, if we look at condensation, of course, it is exactly the opposite process. And so as 1 mole of water vapor condenses to liquid water, you would release 40.7 kilojoules back into the air or back into the surroundings. And that's why we see the negative sign. So again, they're opposites. Now, typically we don't only worry about delta H of vaporization, right? There's one number It's just for the vaporization direction, right? It's a positive value because that's the endothermic direction. And for the condensation, right, it's the same number but negative because that is the exothermic direction. So the heat of vaporization. So we're going to use this heat of vaporization of a liquid to calculate the amount of heat energy required to vaporize a given amount of that liquid. Right? So this is, in other words, a conversion factor. So remember that 40.7 kilojoules per every 1 mole. Right? So if I want to use this in a calculation, I can use this conversion. So I can use this to look at any amount of a liquid because I know, say, if I had 2 moles, right, it would be 2 times this. If I had half a mole, it would be half of this. So for any number of moles of a liquid, I can figure out how many kilojoules of heat it's going to take to evaporate that amount. Now, the heat of vaporization for different materials varies based on what the liquid is, right? And again, this is going to have some tie back to the strength of the intermolecular forces, right? So these materials that have relatively high heats of vaporization, they're going to have stronger intermolecular forces. Remember, stronger intermolecular forces lead to higher boiling points, which means, right, also it's going to mean we have to add more heat to break those molecules apart, right? To vaporize. Once we're at the boiling point, we still have to break those intermolecular forces, and so the stronger they are, the more we're going to have to add. So higher heats of vaporization will occur in molecules that have higher intermolecular forces or stronger intermolecular forces. Now notice these values will vary by temperature. Now we don't worry about this too much. We'll tend to focus on the numbers here at the boiling point. So now we're going to turn our attention to the melting and freezing phase changes, or those phase changes that occur between the liquid and the solid state. Now we're not going to look at these in quite as much detail, but we're going to look at some various aspects of these processes as well. So just to remind ourselves that as the temperature of a solid gets higher, right, the thermal energy is building up. Those molecules are moving, what we might consider vibrating in the solid, faster and faster and faster. And eventually, right, they have enough thermal energy to break or to weaken some of those intermolecular forces to transition from that solid state into the liquid or to melt. Now, remember, we don't have to totally break down the intermolecular forces like we do with evaporation because we're transitioning to a liquid where there's still going to be intermolecular forces. They're just not going to be quite as strong. And so, but we need to break down some of those intermolecular forces so that the liquid state can form, that those molecules can now start to flow past one another, as opposed to being stuck in place as they are in the solid form. Now, just like we saw in the liquid gas, right, once this melting process starts, right, the temperature won't change anymore, right? It will remain at the melting point, or approximately 0 degrees Celsius for water, until all of that solid has transitioned into the liquid phase. So again, if we look at a heating curve, we can see this. So if we take ice that's at, say, minus 20 degrees, and we start to heat it up, right, what we see is that it'll eventually rise in temperature. Once we reach, quote, the melting point, notice that, again, the temperature remains constant during that phase change process. So at this point, any added heat is going to breaking those intermolecular forces necessary to make the phase transition. Then once all of this solid has been transitioned into the liquid phase, then the temperature again can start to rise and we can warm up the liquid. Now, just like we saw with evaporation and condensation, we can look at the energetics here. And so, as we look at the example of putting ice into a liquid, right? When we do that, the ice starts to melt. Right? And of course, the drink cools because melting is endothermic, right? So, just like evaporation is endothermic, right? To go from the solid to the liquid is endothermic, right? We have to break intermolecular forces, so that's going to require energy, or that solid has to absorb energy from the liquid that we put it into in order to melt. That cools down the liquid, and the net effect is, right, we add ice to a liquid, the liquid cools down. So melting is endothermic. Now, of course, since freezing is exactly the opposite of melting, right? It's that transition from the liquid to the solid, it's going to be exothermic. So when water freezes to make ice, heat is released as we form those more intermolecular forces. We release the heat as the ice freezes. Now, this is sometimes hard for us to imagine because it's so cold, right, when this is happening. But as that liquid freezes, right, this gives off small amounts of heat. And so this is one reason why we have to, keep our freezer cold, right? It won't stay cold by itself, right? We have to actively keep our freezer cold by, running a condenser, right, to keep it cold, right? We have to plug it in. We can't just get it cold and then it stays cold, because eventually, right, as this freezing occurs, small amounts of heat get released into the air, warming that air up. And if we didn't recool it, the air would start to warm up within that freezer. Now, just like we saw again with evaporation and condensation, we can quantify this. Now for the melting, we have what's called the heat of fusion. Now, fusion is just the fancy science word for melting, right? We don't call it the heat of melting, unfortunately, right? We call it the heat of fusion. And so it is the analogous to the heat of vaporization. So this is the amount of heat required to melt 1 mole, whereas the heat of vaporization is the heat required to vaporize 1 mole. So to go from solid water to liquid water, you have to absorb, notice the positive sign, you have to absorb 6 kilojoules of energy. Right? Now, of course, the opposite, the liquid going to the solid, the freezing, it's going to be exothermic. Heat is going to be released, but in the same amount. And so we have the negative sign indicating the release of heat, or it's exothermic, and it's going to be the same quantity. Now, one thing to notice here is that the heat of fusion is much smaller than the heat of vaporization. So, for a particular material, we'll always see that the heat of fusion is smaller than the heat of vaporization, because remember, for the heat of fusion, we're not having to totally separate the molecules, right? We're just weakening these intermolecular forces, so it doesn't take as much energy to do that, whereas vaporization, we have to totally eliminate the intermolecular forces. So heats of vaporization will be higher than heats of fusion for materials. So if we look at a table of these heats of fusions, we can see, similar to heats of vaporization, right? that, we're going to see, slightly different numbers in different materials. Now, what we will notice is that there isn't the same kind of dramatic effect based on the intermolecular forces. Remember, for the heats of vaporization, these were quite a bit lower than these materials because the water and the isopropyl alcohol have stronger intermolecular forces. Here we see that they're all pretty much the same. In fact, we have some of these that are even higher than the ones up here, even though their intermolecular forces is weaker. And that's simply because there's more additional factors involved in this freezing, melting process than just the intermolecular forces. But we don't go into those in this book. Now, if we put all these together, right, we put our two heating curves together, if you will, we can build one heating curve, right? So we can see if we take a piece of ice from below freezing and we heat it up. Initially, right, we see the temperature rise until we reach the melting point. So for water, that's going to be around 0. It'll melt, temperature will stay constant until all of the solid has transitioned into a liquid. Then as heat is added, the temperature will rise, so we keep adding heat, it's increasing the thermal energy, the molecules moving faster. All of a sudden we reach boiling, and now we stabilize at that temperature as all of that liquid gets transitioned into the gas phase. Once it's all transitioned into the gas phase, then that steam can again start to heat up. Now, the last phase change that I want to look at is what's known as sublimation. So this one is maybe not as well known to a lot of people, but sublimation is the change from a gas, from a solid to a gas. So the most common example that we usually see of this is dry ice, right? Dry ice is simply solid carbon dioxide. And so, as that solid carbon dioxide sublimes directly into a gas, we get sublimation, right? And when we see sublimation, right, there's no formation of the liquid, right? There's no transition to liquid. We just bypass the liquid, if you will, and go straight from the solid to the gas, right? They do not melt under this particular condition, right? So under normal atmospheric conditions, doesn't matter what the temperature is, right? You can never get dry ice to turn into a liquid, right? It'll go straight from the solid to the gas, right? It'll undergo this sublimation process. Now for dry ice, we know that dry ice is very cold, right? And we put it out at normal temperatures and it immediately will start to rapidly turn into a gas. So a lot of us have seen this. This process starts at minus 78 degrees Celsius, right? So very cold. Right? And this is why if we want to maintain dry ice as a solid, we have to keep it quite cold, because this sublimation will take place even at very low temperatures. Now, of course, dry ice is not the only material that will sublime. Other materials will sublime under certain conditions. Even regular ice. This will slowly sublime at temperatures below freezing, below 0. Now, there's different ways that you may have seen this. You may have actually observed that as the temperature remains very cold outside, below freezing, that over long periods of time, ice and snow lying on the ground will gradually disappear. Now, this is sometimes hard to see, but it's slowly subliming away. Now, you might also see that if you take ice cubes in trays, right, and you leave them in the freezer for a long time, they will gradually get smaller. They won't fill up the cube trays anymore. They'll get slightly smaller, and that's due to, again, to this sublimation that occurs. This is also what causes, ice crystals to form. Like if you put leftovers or food into a plastic bag or maybe even a plastic container, and you put them in the freezer, you can get these ice crystals forming in the bag or the container. And where did that water come from? Well, the frozen water, the ice, either from the surface of the food or interior of the food, has sublimed into the gas phase and then refrozen on the surface of the bag, for example. And so this is why if you leave food in the freezer for a long time, it can become dried out because it's losing the moisture that was part of the food. As that moisture slowly sublimes into the gas phase and then refreezes, that water is in essence being transferred from inside the food to outside the food, and ends up as ice crystals either on the food or on the bag itself. Now, we can avoid this by using something called deep freezing, or what is sometimes just called a deep freezer, where we freeze at a lower temperature. Right? We keep it at a lower temperature because this sublimation process becomes less and less the colder we go. Right? So if we lower the temperatures even lower than a normal freezer, then that food will stay, moist, if you will, right? The sublimation will be less, and so our food won't dry out, so we can freeze it for longer periods of time. Okay, I'm going to close off this section by doing a couple practice problems with these heats of vaporization and heats of fusion. So our first problem here is going to deal with heats of vaporization. So it says, calculate the amount of water in grams that can be vaporized at its boiling point with 155 kilojoules of heat. So if we put in a certain amount of heat, how much water can we vaporize, essentially, is what this is telling me, or asking me. Now, what we know is if we look up, or we're given, that the delta H of vaporization, or the heat of vaporization for water at 100 degrees, is 40.7 kilojoules per mole. So if I put in 40.7 kilojoules per mole, or 40.7 kilojoules, I could evaporate 1 mole of water. So if that's how much it'll take to do 1 mole, how much will it take to do, or how much can be done with 155 kilojoules? So our basic plan of action is, since we're given the kilojoules here, we can use our delta H of vaporization to go to moles of water, and then once we know moles of water, then we can go to grams of water, right, which is what we're asked to, of course, using the molar mass, like we've done many times before. So if we set up our calculation, we start with 155 kilojoules of heat. We're going to then use our conversion factor, right, which says for every 1 mole, right, we want the 1 mole on top because that's what we're trying to find, and we need the kilojoules to cancel out. So this is going to cancel my kilojoules and leave me with moles of water. Now I can continue here, and now that I know moles of water, I can use the molar mass of water, which is 18.02 grams per 1 mole. So this means my moles cancel, and I'm gonna, when I complete this, end up with grams of water. So if I do my math here, I should end up with 68.6 grams of water could be vaporized if I put in 155 kilojoules of heat. Now, and this is not too terribly surprising, right? Because this is almost 4 times the amount that I need here. So it makes sense that I could do almost 4 moles, right? 4 moles would be 72-ish, 18 times 4, right? And so we're not quite that much, but it makes reasonable sense that I could do, many more, several moles, almost 4 moles of water with this 155 kilojoules. So that's one example. So let's do one more problem. Here we're going to work with the heat of fusion, and we're going to kind of go opposite. So in this problem, I want to calculate the amount of heat, right? So what I'm looking for is to find the heat in kilojoules, absorbed in this case, because when 15.5 grams of ice melts, again, at its melting point. So in the table, we can look up the heat of fusion of water, right, which is how much energy it takes to melt 1 mole, right, 6.09 kilojoules per mole, and we can use that in our conversion. So for this problem, we're given the grams, so that's what we're going to start with, and we can convert from grams into kilojoules of heat, right? Again, using our heat of fusion, but there's a part missing here, right? What am I missing? Okay, so let's look, right? I can't go directly from grams to kilojoules because this is not 6.09 grams kilojoules per mole, or gram, it's kilojoules per mole. So before I can do this, right, I first have to take my 15.5 into moles, in this case moles of water, and then I can go, using my delta H of fusion, go to kilojoules of heat. Okay, so now that we have that straightened, let's look at the math. So 15.5 grams of water, or ice. We know that there are 18.02 grams of water per 1 mole. Right, so we're going to divide by the molar mass this time. And once we know moles, then I know for every 1 mole of water, it's going to take 6.09 kilojoules of heat to do that. So if I go ahead and carry out my math here, I get 15.5 divided by 18.02 times 6.09. I end up with so 15.5, so do it with me, divided by 18.02 times 6.09. Sorry. Equals 5.21 kilojoules. Oops, that's not right. That's so high there. Kilojoules are necessary. Now, one thing I will point out here on some of these problems, depending on the table you use, you may get slightly different numbers. So, whereas, one table might give you, 6.09, which is one I looked up. The one I gave you in the notes was 6.02 kilojoules. So use the value that's, that you're given or that's in the table in the book, and it's not going to make a huge difference, right? If I go back and calculate this with 6.02, you should end up with, I think, 5.18 kilojoules. So not a whole lot of difference in the answer, but you will get slightly different numbers depending on sometimes where you find your data. But so now we've seen two problems sort of going in the opposite directions, utilizing these heats of vaporization, heats of fusions to figure out either how much you can change, how much material will go through the phase change given a certain amount of heat, or if you add a certain amount of heat, how much material you can cause to go through the phase change. So we can go back and forth, but one thing we have to remember is we have to work with moles, right? So if we start with grams, we have to go to moles first before we can calculate the kilojoules.